As far as end goals for cryptography goes, we've so far mostly focused on privacy. Symmetric encryption is a way to ensure privacy of communicated data using a shared key. We're now going to approach the second central goal, which is integrity or authenticity, for which in the symmetric setting, the main tool is called message authentication codes. It's closely related to a technique called domain extension, which applies to PRFs as one of the main ways to construct not only these objects, but many other things that we might need. So we'll talk about that as well. So authenticity is in many ways even more basic and application necessary than privacy. If you think about the ability to conduct any sort of transaction over the internet, you need to know who the parties are that are doing it. The problem is to be communicating over a network that's public, where Alice wants to send a message to Bob in such a way that Bob can be sure that the message claiming to be from Alice really did originate with her and wasn't put there by someone else claiming to be Alice. Even if Alice had sent something, the adversary shouldn't be able to modify it and leave it so that Bob still thinks that that modified message came from Alice. So here the adversary is tampering with communication sent over the network. The need or impact of this, again, is fairly immediate when you start thinking about using the internet for pretty much any types of commercial transactions. Imagine, for example, that Bob is a bank and Alice wants to send over a check which pays a certain amount to a third party. And supposing she simply transmits that with no attached cryptography, the adversary, if it has tampering capabilities, can cause damage in a variety of ways. It could change the name of the payee to its own name. It could modify the dollar amount, and so on. So we need some way to make sure that none of these things happen. And the tool for that is a message authentication code. As usual, when we introduce a primitive, we need to talk about both syntax, what types of algorithms constitute it, and security. The syntax here is simple. It's one we've encountered many times before. It's a family of functions. It's simply a two-argument function. The first argument is a key, the second is an input message, and the output is called a tag. The way it's used is as follows. We first, as usual in the symmetric setting, assume that a key has been chosen at random from the key space and is magically available to both the sender and the receiver. When the sender wants to transmit an authenticated message M, she runs M through the tagging algorithm using this shared key to get a tag. And what's transmitted now across the public communication medium like the internet is the message in its original form accompanied by the tag. So both the message and the tag, and this is what the adversary sees. Now the adversary may want to modify the message, but if so, it's going to be forced to try to modify the tag to match, because both of those will be required at the other end by the receiver, who runs a certain verification process to check that the tag here is consistent with the message. This verification process is canonical and simple. All it does is it says, since the receiver knows the key, it simply recomputes the correct tag by applying the tagging function under that key to the received message. And then it checks whether it matches the received tag. If so, it accepts, and else it rejects. So in the end, the whole system is specified just by this one function. We refer to this as sometimes as the MAC, message authentication code, a little confusing because we also refer to this as the message authentication code. or as a tag. So in usage, again, in Word, some of the things we put in the last picture, the sender and receiver share the key, the sender transmits the message together with the tag, and the receiver verifies using the verification procedure consisting of tag recomputation and checking. We can straight away give a definition of security. Intuitively, the goal we're trying to achieve is that the adversary should not be able to forge messages, which means create messages that are unauthentic, not sent by the sender, and yet be able to produce correct tags of them. In the process, we want to allow it to see correct tags of messages that were truly sent by the sender. Even knowing those, it shouldn't be able to create forgeries. So now the formalism uses a game. We let T be the Mac, which is the family of functions, taking a key and an input message and returning the tag. This is the object whose security we're measuring, and it's fixed here. And we have some adversary A who will play this game. It's called UF-CMA, which stands for Unforgeability under Chosen Message Attack, and it's parameterized by this function. The initialize procedure picks a key at random from this set over here, and unlike hash functions, but like key recovery security, Prf security, IND-CPA, this key is secret. It's not returned to the adversary. A set S is set to empty, and this set will be used for some bookkeeping. Now, to understand what we're trying to achieve, it's best to jump over here. The adversary's goal is to output a pair, a message and a tag. This pair is called a forgery. And it wins if the tag is correct, meaning if you compute the correct tag under this key that the adversary doesn't know on the adversary provided message, it matches what the adversary said over here. It somehow guessed this tag without knowing the key. Okay, that's what it needs to do to win. Now, that is an attack mounted on the receiver, but the adversary also has another capability or resource. It can attack the sender in the sense that it can see what the sender transmits, which are correctly authenticated messages, and maybe from those try to learn how to create its own tags on other messages. We capture that by this oracle, which represents the sender. As in many of our cryptographic games and definitions, this is a strong one because it not only allows the adversary to see messages, but to see tags of messages, but to obtain tags or messages of the adversary's choice. So the adversary can submit a message M, and what the game will do is run the tagging function with the hidden key on that message, compute a tag, and return that tag to the adversary. So in this way, the adversary is accumulating correct tags on messages of its choice, and then eventually will go to the receiver and try to forge a tag of some message. If we just left it at that, we notice there's a kind of trivial attack, namely go to this oracle, submit some message M, like the 0 message, and get its tag. Now go to finalize with the same message and same tag, and of course this equation will be true because the tag was created to make it true. But clearly that's kind of cheating and not something that's really violating security, because the message was authentic. The sender did send it and agreed to tag it. It's not a problem if the receiver accepts it. So what we really want for security is that it should be hard to create correct tags for new messages, new meaning ones not authenticated by the tag oracle. The way that's captured in the game is that here we save in the set S all messages which have been tagged. And here we make sure that to win, the message M should not be in the set S. If it is, we declare the adversary to lose. This line is just a sort of possibly redundant check to make sure that your message is in the domain of the tagging function. It's not really valid to even submit something that isn't, so we would usually assume adversaries don't do that, but there's no harm in having that line in there. As usual, whether or not the adversary wins is an event which has a certain probability coming from the fact that there's a probability over the choice of key and maybe also over the adversary's own coins. And we look at that probability, and that's the advantage of the adversary. UF-CMA, again, is the name of the metric. We are measuring security of this particular family of functions, and A is the adversary. Okay, so again, this simply summarizes in writing a lot of what was said on the prior slide, or emphasizes a few points about the definition. The adversary does not get the key K from initialize. It doesn't return it. It's allowed to call the tag oracle with any message of its choice and get the correct tag. To win, it must output a message M or call finalize with M and a tag T. The message must be in the domain, and the tag has to have two properties. It's correct, and the message must be new. So correct means that the tag equals the one the tagging function would return on that message with the key from here. New means the message is not one that was tagged before. The interpretation is that the tagging oracle represents the sender and finalize the receiver, but as usual, our formal definition doesn't have in it any senders and receivers, it's just oracles. And in a word, security says an adversary cannot get the receiver to accept any message that is not authentic, meaning wasn't actually transmitted by the sender. It's a strong requirement because it's not, for example, caring about any semantic aspects of the message that the adversary forges. Even if the adversary manages to get the receiver to accept something that, say, if you thought about it as English text was nonsense, that's okay, the adversary still wins. And a chosen message attack may seem more powerful than something that's really possible, but that's okay, we're being conservative. Let's start thinking about what it takes to achieve something like this. And one small observation is that you need tags to be reasonably long. If tags are too short, you can easily forge by simply, for example, guessing the tag of a message. So this is captured in this exercise by saying that if you have tags of length L, it's easy to design an adversary whose advantage is 2 to the minus L. That adversary would make no tag queries. And so we need L to be large enough to make this negligible. For example, about 80 bits. But usually it's even more. Okay, so let's see how we might start designing a message communication code. As usual, when we come to a high-level cryptographic primitive, we don't do this from scratch. We're going to exploit one of our atomic primitives. And in this case, we'll start using a block cipher. We'll see later also how to use hash functions to build secure Macs. The Mac here is a very well-known one. It's called the CBC Mac. The CBC Mac has a few variants. This is what's called the basic version of the Mac. So we fix a block cipher, for example, AES, k-bit keys, and we let B denote the space of blocks. So it's the set of all strings of length n is 128 for AES. Our message is viewed as a sequence of blocks, so it's in the set B star. We can parse it, break it into blocks as follows, and we let M be the number of blocks. The CBC Mac is a tagging function which takes a key from the same space as the block cipher and a message from the space over here, and returns a tag which is also n bits long. How does it work? Well, as shown in the picture, what you do is something that looks a priori a little bit like CBC encryption. You run your first message block through the block cipher with your key, and you get a result. You then add that in before you add that into the second message block, and then run that through the block cipher again. This is what's called chaining, and gives the name chaining over here. And you continue in that way, and the last ciphertext block here is output. In code, you initialize C0 to be 0, and then you iterate this operation, where the next ciphertext block is the block cipher with this key applied to the prior ciphertext block and the current message block. And if you want to think about or relate to CBC encryption, as we had studied earlier, the difference is that encryption doesn't use a 0 initial vector but a random one, and outputs all the intermediate blocks. But tags are compact. No matter how long the message, you want a fixed length tag. Okay, we now have a candidate message authentication code, and we have a metric UF-CMA under which to verify it. And let's see, does it work? Well, actually it doesn't. This basic CBC Mac is breakable. There is a way to violate UF-CMA security, and it works as follows. So remember, the adversary's goal is to create the correct CBC Mac of some message. It can choose any message it wants. And it has to do that even though it doesn't know the key. So not knowing the key precludes it from actually running through the algorithm on its own. The adversary as a capability has the ability to go to the tagging oracle and get tags of messages of its choice. So here's our adversary specified in pseudocode. It starts by picking some one block message X and calls the tag oracle on that. And that gives it a tag we'll call T1. Okay. Pictorially then, when you have a one block message, the tag is simply the result of the block cipher with key K on that message. If you look at the CBC Mac, that's the case when M here is 1, and you have one iteration here, and this is 0 when you start, and so you just get the block cipher on the message. Fine. Now the adversary wants to construct some other message. It can't use the same one, but any other message for which somehow it knows a valid tag. It's going to construct a 2-block message whose first block is the X, and second block is this tag XORed with X. Why does that work? Because look what happens when you compute the CBC Mac on that. When you start, you go through the block cipher for this block here. You chain, you add this in. But this addition, because T1 is here, the T1 goes away and X goes back. And the tag of X, of course, or the result of the block cipher on X, is T1. So the adversary knows that, and it can predict. So it knows T1, and it knows T1 will appear over here. So it says, okay, if I take this message, its correct tag will indeed be T1. And that's true, and hence this adversary works and has an advantage of 1. Okay, this is called a splicing attack because you kind of splice together two blocks, if you like. This is just a summary. We have an adversary shown here. It has an advantage of 1. It's efficient, and so the basic CBC Mac is not secure. Now, before we dismiss it, it's maybe worth making one remark. In this attack, the query was a 1-block message, and the forged message was 2 blocks. This is crucial to the attack. In other words, you have to be able to authenticate on messages of a certain length and forge on ones of a different length, if we made the restriction that the MAC can only be used for messages of some fixed number of blocks, whatever that may be, 1, 2, 5, 10, it turns out the basic CBC Mac works. And this will be important at some point. So, given that the basic CBC Mac there failed, and given also that we identified an important reason for its failure as being the ability to vary the length of the messages being authenticated, what people sought is a way to patch it to avoid that. And one way to do that is to somehow involve the length or number of blocks of the message into the MAC. So here's a natural thing to try. You construct a new message authentication code. It, as before, breaks the message into blocks. But now it appends to the message the number of blocks in the original one encoded as an n-bit string. And then you run the CBC Mac, original basic CBC Mac, on this expanded message. And you return the corresponding tag. So the hope here is that involving the length in some way is going to defend against the attack we saw before. So involving the length is a good idea, and it's getting at the right problem, but it turns out that this particular way doesn't work. So interestingly enough, the exercise asks you to give an attack on this method and prove that you can violate UF-CMA security. This is another exercise, and in this case, it's your job to determine if it works or not. Again, it tries to involve the length of the message in some way and then perform a basic CBC Mac. And what it does here is in the initial vector, it puts in something related to the length. And see if you can figure out whether this works or doesn't. In practice, we are worried about an attack called replay. So suppose that Alice transmits a message and tag to a bank where the message was some financial transaction. She's using a good message authentication code, so T1 is the corresponding tag. And the adversary has no way to create tags for any messages that are new, meaning different from M1. And we have in our games said that's what we want, that's what security means. But here's an attack that doesn't violate that security definition and yet is quite damaging in practice. Having captured this, the adversary just resends it. What happens is that the bank doesn't really realize that it's already been sent before and simply credits Bob twice, and that continues. So in this way, there are many such situations where replays create security vulnerabilities. And the question then is, why is our definition of security not asking for that? Our definition says that if the adversary were to output as a forgery a message whose tag it had already seen through the tagging oracle, we don't declare it a win. So this would not be considered a violation of security. Well, the reason is not that we don't think replay is important, but rather it reflects a kind of modular design. In practice, it's easier to address replay as an add-on to message authentication, and you do it either using timestamps or synchronized counters maintained between the two parties, and there are many such methods out there. So given that, we will continue to use UF-CMA as our target and to ignore the replay problem. Okay, so far we saw some example or candidate attempts to build a message authentication code that was secure, all of which failed. So we still don't have something that works. So let's approach getting that. And it turns out that a convenient way to do that is to actually shoot for something stronger we're going to notice that if you have something that's PRF secure, it's automatically UF-CMA secure. We can then leverage that in a few ways. One is that we already know some things that we believe are PRF secure, so we have a few examples of Macs from that. And then it will motivate us to build more and different kinds of PRFs. So let's start with this result. If I want to show that given some family of functions f, assuming it's PRF secure, it will also be UF-CMA secure, we would capture that in a way we have studied before, which is by some reduction-based theorem and proof. So we take the following form. We let f be some given family of functions and consider an adversary trying to violate its UF-CMA security. That adversary has some resources, queue tagging Oracle queries, and a certain running time, and it'll achieve some advantage. I want to somehow show that this advantage is small due to my assumption of PRF security on the same function family. That is done by constructing a PRF adversary B from A such that this equation is true. Here we are saying that the UF-CMA advantage of A can't be much more than the PRF advantage of B. Maybe a little more, 1 by 1 and 2 to the n, but n is big and that's not really going to matter much. So if PRF security holds, then this is small, and since this is also small, this will be small as well. Okay, now there's also a question of resources. For something like this to be meaningful, B needs to be about as efficient as A. When we consider the resources of B, we have to ask about Oracle queries. Its Oracle is Fn. Remember, in the PRF game, you have this Fn Oracle. The number of queries to that is one more than the number of tag queries made by A. And the running time of B is about the same as that of A. So this theorem then, again in summary, is simply saying PRF implies Mac. And we will leverage it later. But let's now just look at how we might establish it, meaning how the reduction works. So in the reduction, our job is to build the adversary B. B is a PRF adversary. It's playing the PRF games. It has an Fn Oracle, and it's trying to distinguish whether it's playing the real game or the random game. As usual, you think about it as writing an attack. You're trying to violate PRF security. How are you going to do that? Given that we don't know anything specific about the function family f whose security we're trying to violate, the reason we can do that is we exploit that we have already given an adversary A who violates UF-CMA security, and we're going to exploit an A by running it as a subroutine. And intuitively in one line, the way it works is that B is simply going to see whether A can violate UF-CMA security. If it does, it says, I think I'm in the real world. And if it doesn't, it says, I think I'm in the random world. And the intuition behind that is that in the random world, it would be very hard, in fact, impossible except with tiny probability to violate UF-CMA. So let's see how that plays out. So adversary B begins by initializing a set to 0, and now starts the main thing. It runs adversary A. Adversary A will trundle along and deliver, as it's supposed to, a forgery attempt, a message and what it claims is a correct tag. But in order to run, adversary A needs a tag oracle. If you just start running it, the first thing it might do is say, here's my query to the tag oracle. Here's a message, give me the correct tag. And there's no real tag oracle in this world because B is executing A. So B has to provide an answer. In other words, B has to provide a simulated tag oracle. So it does that here as a subroutine, and it's quite simple. Remember that B has an Fn oracle. So what it does is it calls that on the message that A requests to its tag oracle, gets a result, and it simply returns that result back to A and says, here's your tag. For its own internal need, it records the message that A queried to its tag oracle. Okay, so now A will continue and it will output this message in tag. What B now does is it says, I want to determine whether or not A succeeded, meaning whether this forgery is valid and whether A would win the UF-CMA game. So I need to know, is T the correct tag of M? So how do I, B, determine what the correct tag is? Well, I'll just call my own FN oracle. After all, that's what tags are as far as A is concerned. So I call that on this message M here to get some T prime, and I check whether T equals T prime. But that's not the only thing that determines whether or not A wins. The other is that M is not something it queried to its own oracle. So B needs to check that too. It checks that M is not in this set S. If both conditions hold, then A has won the UF-CMA game and B sets its output bit to 1. In other words, it's going to claim, I think I'm in the real world, not the random world. But if it fails, it says, okay, I think I'm in the random world. And it returns that guess. Okay, so that's our description of the adversary B. And now we have to justify the claims that relate the advantages of A and B as in the theorem statement. So we do that in steps. First of all, in evaluating the Prf advantage of B, we recall that it's the difference in the probability of returning 1 in the real game with B and in the random game. So we look at those in turn. So we recall here the real game, which is associated to a function family F. The game would pick a key at random, and the FN oracle, which B gets, simply returns the result of our function family under this key applied to M. The main observation now is that this oracle and the tag oracle that adversary A expects behave identically. After all, what does the tag oracle do? It also, under some hidden key, returns F sub k of M. So only the name has changed. Since tag sim, our way of simulating the tag oracle, is simply calling Fn, we are returning responses that are exactly what A expects. They're correct tags. So from A's point of view, it's running in the UF-CMA game. Everything looks just dandy. And so it will output its forgery, this message tag pair, the same way as it does there. And that forgery will be correct in this, and A will win the UF-CMA game exactly when B returns 1. Because remember, what B does is check that the A's output is correct and new, and that the UF-CMA game was 1. So the probability that B returns 1 is exactly the probability that A wins the UF-CMA game. Now again, this probability and this probability are in completely different experiments, but nonetheless there's this relation, and we've managed to link PRF and UF security across these different adversaries. We still have to look what happens when B is running in the random game. In that game, which is associated to the range set of the function family F, the procedure Fn is still there, it has the same name, but it works differently. When you give it a message M, it just picks a random n-bit string and returns it, of course making sure that it stays consistent with whatever it picked in the past. So we now want to know our adversary B, whose pseudocode we saw a few slides back, when you run it in this game, what is the chance that it outputs 1? So if you look back at that code, you see that what B does is it obtains this forgery from adversary A. And then it returns 1 under 2 conditions. The first is that the message is not an S. And the second is that an equality holds between this and this T over here. Okay, so we're interested in when 1 is returned. So it can only happen if M is not in S. So assume that's true. What does that tell us? Well, in the process of execution, B has called its Fn oracle and obtained some random strings. Those were used to simulate the tag oracle that A expects. However, if M is not in S, it means that Fn has never been called before on the message M so far. That means that this string here is a completely new, fresh, random string because the game is going to pick it afresh. And hence, since T at this point is already chosen, the chance that T prime equals T is at most 2 to the minus n. And since the adversary B returns 1 exactly when T prime equals T and M is not in S, the chance it returns 1 is at most 2 to the minus n. Now, one has to go over this argument a little bit and kind of make sure one understands it and checks various things. For example, B is providing A with an oracle tag sim that's supposed to represent A's tagging oracle. In this game, that simulated oracle is returning random stuff back to A, and that stuff does not look anything like what A would expect. What is A going to do about that? The fact is, for this analysis, we don't care. The only thing we care about is that A will output something, and the chance that the tag T here equals T prime is going to be 2 to the minus n. And that's enough to get this conclusion. We can then put that together. So here I've just showed our adversary B again. And we can now compute the PRF advantage of B. By definition, the difference between the probability of returning 1 in the real and random worlds. And we have computed both of these individually, so we just plug it in. And now if you take this equation and just shuffle terms around, you get the equation in the theorem statement. Okay, so that concludes our proof. And we've now seen that PRF security is stronger than UF-CMA. If we can achieve that, we have UF-CMA for free. Once we've done that and related PRF to UF-CMA, there's a natural, theoretical at least, question that comes up. Are these two the same thing? What about the converse? Is it true that UF-CMA security always implies PRF security, or are they different? And it's an interesting exercise to show that the converse of the theorem fails. UF-CMA is strictly weaker than PRF and does not in general imply it. So what do we mean by that? Let's try to show why this is true, not just for the conclusion, but because the method here is kind of generic and is a nice way to understand different metrics of security and how they relate to each other. If I want to demonstrate that this implication fails, it's not a reduction-based proof I'm looking for. What I'm looking for is a counterexample. I'm not saying that all functions that are UF-CMA fail to be PRFs. When I make this statement, I'm saying it's not true in general. That means there exists a counterexample. So I want to exert a counterexample, which is a specific function family F, which is UF-CMA secure, but fails to be PRF secure. Okay, that's what I'm shooting for. What that means is that it's up to me to design the function family. It's not something arbitrary or given. I actually have to make it up. So we now ask ourselves, how do we create an F with these two properties? So if we were to try to do this from scratch, we wouldn't get very far, just because it would be rather hard to just achieve one. We already know that it's not that easy to build something UF-CMA secure. So how are we going to get around that? The template and approach we're going to use here, which is typical to these counterexamples, is assume I start out with some function family which is UF-CMA secure. I don't have to worry where that comes from. I've been given that. If I have no such function family, this whole question becomes moot. So I may as well assume that some such family exists. And to build my family F, I'm just going to modify this F prime a little bit you can think of it as building in a bug. I want to modify f prime so that its UF-CMA is preserved by f. So I don't want too much of a modification. It's got to be small enough that UF-CMA security doesn't go away. And yet it has to be significant enough that PRF security fails. So now we have to think intuitively, how can we do that? What is the intuitive difference between PRF and UF-CMA? Well, what it is that PRF outputs look random. They don't have structure. And that is quite different from the ability to produce the full output or not, as UF-CMA looks at. So let's do the following. How do I design F? I first, given a key K and message M, run the given F prime and get this tag T prime. I simply then append to it a 0 bit and use that as the output of F. Why am I doing this? Because a 0 bit is structure. It's not random looking, it's always 0. On the other hand, the presence of T prime should mean that as far as creating tags goes, this is not too different from F prime. So this is my suggested counterexample. In this counterexample, the output length L of F is 1 more than the output length of the given F prime. Okay, let's now justify that this works. What does that mean? I have to check these two properties, that F is not PRF secure, but it is UF-CMA secure. So let's do that. We'll begin with the second, because that kind of is the whole point, is that we're trying to show something that does not have PRF security. So if I want to show that PRF security is violated, how do I do that? Well, I need to give an attack. So this attack is an adversary. It plays the PRF games, the real and random games, and it achieves a high advantage. So intuitively, how does it do that? Because in the real game, it sees outputs of F, and those always end with a 0 bit. In the random game, the things it gets are not always going to end with a 0 bit. It'll only happen half the time. How do we encapsulate that into an adversary? It picks some message in the domain and calls its FN oracle on that to get a tag T. It then looks at the last bit of T, the least significant bit. And if that bit is a 0, it says, I think I'm in the real world, and otherwise it says, I think I'm in the random world. That's our attack. Now we need to assess how well it does. So first assume we're in the real game. In that world, the FN oracle is returning F sub k of M for some key K that the game chose and that A doesn't know. However, we defined F sub k of M earlier, and remember that no matter what input you give it, the last bit is always set to 0. So this bit will be 0 with probability 1. So A will return a 1 with probability 1. Now we turn to the random game. In that case, T here is just a random string of what length? N plus 1 bits. Remember, that's the output length of F. If it's a random string, its last bit is also random. So the chance that that bit is 0 is just a half. And so A will return 1 with probably a half. Okay. And now subtracting those two, we get the advantage, 1 minus half, which is a half. And that's high. Breaking something with 50% advantage is extremely high. So that's a nice valid attack. By the way, as a small exercise, you could ask yourself how to modify F to reduce this from a half, say, to anything else you want, like to do the negative 100. Okay, that's the first claim. Remember, the second claim is that F is UF-CMA secure. Now, that claim is not unconditional. What we're saying is that we assumed F prime is UF-CMA, and that UF-CMA is inherited by F. So we're saying UF-CMA of F prime implies that of F. Statements like that are established how? Well, by the same proof-based technique we've used many times, which is by reduction. So let's formulate a claim capturing this more precisely. That claim would say, suppose I have some adversary attacking UF-CMA security of F. It makes some number Q of tag queries and has some running time, and it achieves some advantage. I'm going to construct another UF-CMA adversary A prime, but this will attack the UF-CMA security of F prime, our original function family. And it will achieve some advantage, which will be at least this. So this advantage is bounded above by this one. As usual, that implies what we have here, because if we assume F prime is secure, this is small, and now this is small, which implies F is secure. So here we are looking in both cases at UF-CMA, but the function families are different, F here, F prime here. This adversary A prime is about as efficient as A, same number of tag queries and about the same running time. Okay, so let's do it. We have to design this A prime. As usual, we give pseudocode for it, and we have the usual kind of reduction set up. So what does A prime do? Remember, it's trying to violate UF-CMA security of F prime. So it has in its hands an adversary violating UF-CMA security, but of F, and it needs to exploit that. So it runs A to get a forgery M and T for relative to F. In order to run A, of course, it must simulate the tag oracle that A expects. So let's take a look at how it simulates this tag oracle. Now, taking a bit of a higher level view, there's only a small difference between tags of F and F prime. Those of F have an added 0 at the end. So we kind of know we'll be playing around with that 0. But the delicate thing that we have to pay attention to is that sometimes we have to add a 0 on and sometimes we have to strip it off. And let's see how that plays out. So A here is expecting an oracle producing tags for F. F is our constructed function, which always has a 0 bit at the end of every tag. A prime's job is to supply those tags. It does that via this simulated process captured in this subroutine. When A submits query M, A prime goes to its tag oracle and gets a tag T prime. T prime is a tag for F prime, and so it's the shorter one. To create from this a tag for F, which is what A wants, I append a 0, and that creates a tag for F, which will satisfy A. So now A is happy, trundles along, and eventually outputs a forgery. But this forgery is for F, and it's a message and a tag which are correct for the F function. But A prime is looking for a forgery for F prime. What's the difference? The F forgeries have a 0 bit at the end. So I need to drop that bit. So now what A prime does here is it truncates. It takes the first n bits of this tag and outputs that as its tag for against F prime. Okay. So you may have to check the details a little bit, but again, the sort of delicate element is here you append the 0, here you drop the 0. Okay, but just at a high level then, where are we so far? We've shown that Prf security implies UF-CMA security, but the converse is not true. So now we go back to the task of building secure UF-CMA families, but the way we approach this is let's just build PRFs and then use that prior result to get UF-CMA security. It turns out in practice this works well enough. The first response one may have to that is, but we already have PRFs. What? Well, AES, right? We've already said we are willing to think that AES has PRF security, of course, up to the birthday attack, but we're fine with that. That's true. That gives us a MAC. The difficulty is that it would be a MAC on messages of length 128, and that's not what we want. we want Macs to be able to take messages of arbitrary length. That leads to a problem we call Prf Domain Extensions. So suppose we have a family of functions taking a key and some input in some domain and an output in some range. There are two kinds we might consider. One is what's called fixed input length, that the domain is a set of strings of some fixed and usually small length. Or it could be variable input length. That means D is a large set, perhaps a set of all strings, or perhaps the set of all strings with some constraints. The length is allowed to be big, but there is some upper bound. Maybe the length has to be a multiple of some block length, various things like that. So this is what we really want, variable input length function families that are UF-CMA secure, or even better, Prf secure. So what we are given then is PRFs that are fixed input length in the form of block ciphers, or possibly compression functions if we're willing to think about them also as PRFs. And so the problem we have, which is domain extension, is turn a fixed input length PRF into a variable input length one, and do this in a good way so that security is provably transferred. Prf security of this one implies Prf security of this one. So that's a nice little abstract problem, and let's consider methods to do that. Well, we already saw one. The basic CBC Mac is in fact a candidate construction because it starts from a fixed input length PRF, namely a block cipher, and tries to construct a variable input length one. The only problem was security-wise, it didn't work. So we want something different, but of the same sort of type. And so here are a few solutions we'll discuss. There's the Encrypted CBC Mac. There's a standardized version of it called Cmac. And then there's Hmac, which is one based on hash functions rather than block ciphers. So here's what the Encrypted CBC Mac does. Now, again, we see reflected here the same sort of principle or idea we've seen before, which is that when something didn't work, we don't throw the whole thing out, but somehow we find that there's a small modification that fixes it. So we start by going back to the basic CBC Mac, and we extend a little bit. In the Encrypted CBC Mac, we again start from some block cipher, and now our Mac has a key which is two block cipher keys, so the key length has doubled, and we write our key as k in and k out, the two parts. How does it work? Well, it breaks the message into blocks as usual, and let little m be the number of blocks. Then it computes the basic CBC Mac just as before, using its first key k in as the key for the block cipher. And that will get it up to here. If it simply output this, it would be the basic CBC Mac, and that wouldn't work. All that it does is it processes this again with the block cipher under this other key. And that's it. So, and that is the output of the Mac. Here it's just written in code, which is just, this is the for loop for the CBC Mac. This is the last step. Okay. So then this is called encrypted because this is viewed as encrypting the CBC Mac output. And this is something we now need to assess. So our hope or claim is that it works, but we should think about it and be a little careful. Once we start approaching an analysis of its security, we notice that there is an attack, and this reflects again something we've seen in many instances before, which is that there is a non-trivial attack based on the birthday paradox or the birthday problem. This violates UF-CMA security using a number of tag queries that's kind of less than you might intuitively expect. So if you look at the number 2 to the power half the block length, then it's possible with that many tag queries to violate UF-CMA security. Okay. Now, this is not something I'm going to demonstrate the attack for. It's not entirely obvious. In fact, it took some time to be discovered in the research literature. The reason is that merely using the birthday problem allows you to detect the difference between random and non-random behavior, but doesn't lead to forgeries. And that's the little extra step you have to take here. So it turns out that these birthday attacks apply to a large class of Macs based on what are called iterated designs. And that includes all the ones we look at here, the Encrypted CBC Mac, Cmac, Hmac, and many others. But the way we get around them is that the cost of the attack, 2 to the power half of this output length here, is rendered high by simply making that output length big enough. For example, when you're using AES, this would be 128, so this is 2 to the 64, and we consider that prohibitively large enough. However, for this same class of Macs, we are usually able to provide theorems saying that these birthday attacks are effectively best possible. And thus, that gives us some confidence in using them. So, and we've seen this kind of picture before for encryption. So these iterated Macs iterate some lower level probability. It could be a block cipher or a compression function, as we'll see later. So this is simply an exercise suggesting that you try to find these attacks that use the birthday phenomenon to violate UF-CMA security. Okay, so let's now state a theorem that summarizes the security of the encrypted CBC Mac. So, and intuitively, it's just saying that the birthday attack is best possible. So we fix our block cipher with B being the set of possible blocks, let's say of length, which are all strings of length, n, where n is the block length. And F is our encrypted CBC Mac, whose code is repeated here simply for completeness. As usual in a reduction-based proof, what we're going to say is we're handed an adversary against the encrypted CBC Mac. Now remember that at this point, we are not going to need to look at UF-CMA. We can do everything in terms of PRF. Because PRF implies UF-CMA, we're going to just establish PRF security of the encrypted CBC Mac. So we have this PRF adversary. It's using some resources, Q Oracle queries. And since the lengths of messages here can vary, we need something measuring that. And what we look at is the total number of blocks in the messages across or summed over all those queries. And finally, there's some running time. So that will result for A in some advantage. It'll achieve some advantage in violating PRF security, and I want to upper bound that. How do I do that? I construct an adversary D, which is attacking the PRF security of the block cipher E. And that it will have some advantage, and that will be here, plus some other term. This other term intuitively is the success probably from the birthday attack, which is unavoidable. So you can read the theorem as saying, yes, we have to give up that, but this is small and we're not giving up much more as long as E is PRF secure. And D is about as efficient as A. Now, although I've been speaking of a block cipher because that's usually what we use, the theorem doesn't require it. It's a family of functions that doesn't have to be a block cipher. So that can, in some cases, yield some, or make some difference in the security that you get from this. Okay, so this theorem then says, in summary, that the encrypted CBC Mac is good. We're not going to try to prove that. There's a few steps involved in that. So let's try to here get a sense numerically of what kind of security you would expect now from different encrypted CBC Macs or even other Macs based on what we use to instantiate them. Because there are many choices. For eCBC, you pick the block cipher. You have either DES or AES or others. For Hmac, which we'll see later, you can pick the hash function, SHA-1, SHA-256, whatever. So the way we're going to analyze it is assume that all messages that we are authenticating are M blocks long and that there are Q of them. So we want to authenticate this many messages. And if you look at the theorems, the formula is that roughly the number Q of such messages that can be authenticated is this: 2 to the power half of the output length of the Mac divided by the number of blocks in the message. So it decreases as messages get longer, which is kind of what you might expect. And what we're looking at here is, how does this play out numerically? Well, if you pick DES as your block cipher and use the encrypted CBC Mac, the value of N, the output length, is 64. That's the block length of DES. So let's see what happens. As an example, suppose you're looking at 1024 block messages. This says I can only authenticate about 2 to the 22 of them before things kind of fall apart security-wise. So not too much. What if I move to AES instead of DES so that the output length goes up to 128? Keeping still the number of blocks in a message at 1024, I see a big jump in the number I can safely authenticate towards the point where, in practice, this ought to be enough. This shows you the advantage of switching to a block cipher with a bigger block length. What if I had longer messages? For example, if I had messages of length 10 to the 6 blocks, which means about 16 megabytes, then this drops. I can now authenticate a smaller number of them, but still a very large number. We're doing okay there. Let's now consider Hmac, and let's first use SHA-1. In this case, the output length is the output length of SHA-1, which is 160 bits. Even with these much longer messages, I see that the number I can safely authenticate has gone up. It's now 2 to the 60, which really should be enough for any reasonable application. If I were to use SHA-256 with Hmac, where the output length is 256, for those long message lengths, I would have an extremely high number of messages I can authenticate. So this is an illustration also of how you use these results and the numbers and bounds in them to determine what are the limits in your applications for things like how much data can I actually encrypt before things become insecure, and how the theorems we give enable you to answer questions like that. Okay, so we're now going to get into some more practical matters which arise when you're actually trying to implement message authentication codes. And these are interesting because often they come at the boundary of implementation and crypto. And due to this, there can be errors. And it's interesting and valuable to extend our cryptographic treatments to deal with them. So if you look at our schemes, you see that in something like Encrypted CBC Mac, we assume that messages have a length that's a multiple of the block length of the block cipher, because we had to break the message into blocks and then do some iteration. And let's use the term full for any such message. But the problem is, in practice, there's no reason to think messages are full. If you have a real message, which is an email or a video or something like that, it can have arbitrary length, not a multiple of, let's say, 128, which is the length of the block cipher. So an implementation has to figure out some way to deal with that. So as an illustration, we're going to use messages whose length is a little more than 2 blocks. Think of it as 2 full blocks and then a little bit more. Okay, but why is this a problem? We sort of have an obvious approach to solving this, which is padding. just pad on and then use a normal Mac. The intriguing thing is that padding affects security, and how you pad matters. The obvious way to pad is just pad with zeros. Throw in enough zeros that the last block becomes full. It becomes 128 bits if that's the underlying length of your block cipher. But if you do that, I claim that you have an insecure Mac, right? And here's an attack that shows it. So this adversary is going to first request the tag of the message that has 2 full blocks, both equal to all ones, and 1 0 at the end. It gets that. Now it says, consider the message which is the same full 2 blocks, but 0 0 at the end. This is a different message. I should not be able to create its tag, but I can, because it's the exact same as the tag here. Why is that? Because when this message is padded, I will get 1 to the n, 1 to the n, 0 to the n, and that's what actually gets tagged. And when this message is padded, it's the same. You again get 1 to the n, 1 to the n, 0 to the n. So the tags are the same. Okay. So this is not a good way of tagging. What is a good way of tagging? What's often done is you put a 1 bit and then you put enough zeros to bring the length up to the block length. So that's good, that works. It turns out that with that padding method, one can show that security is maintained, meaning if you started with a message authentication code that was secure when messages had a length that's a multiple of the block length, it continues to be secure when that length restriction is dropped and we have arbitrary length messages. Good. But then in practice, people find that this has a cost and we have to pay in performance. Why is that? Suppose that I had a message that was already full. It had 3 blocks and it had a length which is a multiple of the block length, and so these are all full blocks. What happens with the padding? So it turns out that for security, you cannot drop it. You're forced, in fact, to put in a 1 and enough zeros that you create a whole extra block at the end of padding. Security-wise, that's fine, but performance-wise, it means you have one more call to the block cipher. And that may not seem like much, but think of short messages, let's say in this case, and you were hoping to have 3 calls and you have 4, so you have what, like a 33% extra performance cost. And that's not that desirable, especially because short messages are quite common in packet authentication and things like that. So all these considerations led cryptographers to ask, well, can't we optimize these designs? And one way certainly was to handle length variability and non-full messages much more cheaply without these extra block cipher invocations. But there are other issues. For example, the encrypted CBC Mac already had an extra block cipher call. That was the encryption. Remember, it had 2 keys. It performed the basic CBC Mac, and then it had this extra block cipher call. So when you add that on, it's kind of like there are 2 extra calls compared to the basic CBC Mac, which is what you'd like in terms of performance. And so the question is, what can you do something better on the design front? So can we get a better message authentication code? And so this has been tackled, and there's a construction called Cmac, which is now a government standard and captured in this document and also in various RFCs. And this can handle messages of variable length and non-full messages directly, and it has minimal overhead in terms of performance and other nice features. For example, unlike the CBC Mac, there's only one block cipher key. The key length is kind of what you'd like, optimal. And nonetheless, the security is the same as for eCBC. We can't avoid the birthday attack, that happens, but there's that security proof showing there's nothing better. Okay, so this is a nice story about how cryptography evolves to bridge the gap with what implementations want while preserving not just security but even proofs of security. We can quickly take a look at how Cmac works. It uses a bunch of neat little tricks. Okay, so start with our block cipher, which in practice may be AES. So the key length and block length is the same in this case, and it's set to n. Let's let CBC sub k of m denote the basic CBC Mac. That means that the message here must be full. Its length must be a multiple of n. We know that by itself this isn't secure, but we'll still use it as a subroutine. Okay? And this uses the block cipher E. And we'll fix a constant j. So what Cmac does is if you give it a key k and a message m, the first thing it does is it uses a key generation subroutine to derive a couple of subkeys k1 and k2. How does it do that? It runs the block cipher on the 0 message. This is 0, n bits of zeros to get a key k0. And then it creates k1 by shifting k0 by a bit, rotating it. But depending on the most significant bit of k0, if that bit is a 0, k1 is k0 shifted by 1, left shifted, and shift, as it says here, means that the most significant bit vanishes and the least significant becomes a 0. But if the most significant bit of k0 was a 1, you have a different choice of k1. It's that shifted thing plus this constant. You create k2 by the same formula, but starting from k1 over here. If its most significant bit is 0, you do this, else you do that. And these are your two subkeys. Now, why these two bizarre operations? Mainly because they're extremely fast. So they use native instructions in the processor, and so they're extremely cheap to execute. Okay, at this point we have our two extra keys. What do we do with them? So now we come to the full Cmac algorithm. Given a key k for the block cipher, so note that there's just one key for the block cipher and a message m. Remember, the length of m could be anything, not a multiple of the block length. What does it do? It first runs this to derive these two keys k1 and k2. Now in an implementation, you would do this just once. So although the formal description of the algorithm has this as a step, you would actually have done it in pre-processing and cached these values. Now it takes the message and breaks it into blocks. Except the length is not a multiple of the block length, so the last block could be short. It has length less than or equal to the block length. Okay, and that length will be denoted by L. So L is some number between 0 and the block length, which is the length of our last block. Now remember that one of the cost hits that we got from the 1,0 star padding method was that when L was equal to N, we did extra padding for security. The way Cmac avoids that is it says when L is equal to N, we're going to do something different. We're going to take that last block and offset it by one of our keys. So we add key material to it. Okay, and otherwise, we're going to offset it with a different key. Otherwise, now the length is not n, so this is actually short of n bits, and so there's room to pad. So we do the padding the same way as in the 1,0 star method, but this will not create an extra block because L is strictly less than n at this point. So there may be no zeros here, but there is place for the 1, and if L is a lot smaller than n, then enough zeros are thrown in. Having modified the last block in this way, we consider the message m here, where we simply replace this block by our updated version. Notice this is now a full block. It has length n because it either did here or was made to through this. And on this, we simply run the basic insecure CBC Mac. And the claim is somehow this works. Even though message lengths vary, this will actually work. Now, as I mentioned earlier, this algorithm is a government standard. It's kind of interesting maybe to take a look at that. So this is the document put out by the National Institute of Standards, Special Publication 838B, and it describes the Cmac mode for authentication as part of a recommendation for block cipher modes of operation. And one can look at the description in here, and you'll see it quite carefully written out so that implementations know exactly what to do, and there will be descriptions of all the building blocks and the algorithm, and this nice little picture which shows the two cases we saw of the algorithm in our slides, when the last block is full and when it isn't. CIF is the cipher which we denoted by E. Okay, so so far we've looked at constructing message authentication codes, or PRFs, with large domains using block ciphers. In the early 90s, that meant DES, and with an increasing need for authentication for packets on the internet and applications of that form, there was a perception that DES was too slow and something faster would be desirable. At that point, hash functions were starting to come in, the MD5 series, and they were faster than DES in software. So a natural question that arose is, why don't we use hash functions to build MACs, message authentication codes? Good idea, but there's one immediate difference. Hash functions are keyless. Now again, this refers to things like the pragmatic MD SHA series, and which don't have a key. Even if hash functions have a key, it's considered public, so that doesn't make too much of a difference. So in some ways, the question then became, how do we get a key into a hash function so as to make a secure message authentication code? And there's an obvious way you might consider doing that. So let H represent our hash function, which at that time was MD5. And when you want to create a MAC, which is a function family here taking a key K and a message M, just prefix the key to the message and hash it. And then you can ask whether this satisfies UF-CMA or PRF security. And it's a plausible design, and what's interesting about what happened subsequently is that a weakness was discovered, but knowing that weakness required understanding the underlying structure as arising from the fact that these hash functions were being designed using the MD paradigm that we studied earlier. If you hadn't known that, you may not have noticed this attack. But knowing that, we know that actually there's a compression function being iterated to implement the hash function. So let's see what happens when you open up this internal design and see what happens when you're running the hash function on input K concatenated with the message. Remember that it breaks the message into blocks, eating up one block at a time with the compression function. For simplicity, assume K is one block long. So that from the point of view of the hash function, it's just data, and it's the first block of the data. The second block of the data from the point of view of the hash function is what for us is the first message block. And that goes into the second compression function iteration, and you continue like that. And then remember that MD will append before it ends the number of blocks in the data and use that itself as a block. From its point of view, this has m+1 blocks, because this is also just one of the blocks. And so m+1 goes into here. And this is what comes out. Now, knowing this, I claim that we can notice a forgery attack, a way to violate UF-CMA. How do you do that? Suppose you have obtained this MAC or hash value, meaning you went to your tag oracle, gave it the message M, and this is what you got back. I now will create the MAC of a new message. I do that simply by observing that the compression function, after all, is completely public. What if I ran it using this as the chaining variable and this, the number m+2 rendered as a block, as the message block? I claim that the output is the hash of the key concatenated with a new message m prime. That message simply being this over here. So m prime is m concatenated with this rendered as a message block. If you compute it, the hash of k concatenated with m prime, you just do exactly this picture and you end up with here. This appears because the message m prime has m+2 blocks. Or in equation form, you could write it like this. And so this means that I have a forgery attack violating UF-CMA with one query. So that was the end of that suggestion. Now, this was the impetus for the design of Hmac, which became a very popular construction and standardization and usage. And so how does that work? It also uses as a building block a hash function, such as MD or SHA, and assumes it was built using the MD transform. So to start describing it, let B be the byte length of a message block. So we've typically talked about message blocks in bit lengths of, say, 512, but that's 64 bytes. And N is the output length, and this byte length has to be at least n over 8. Now, the design will use a couple of constants called IPAD and OPAD, and this is the byte 36 repeated B times, and this is the byte 5C repeated B times. So here's what it looks like. And we see here again something we've seen many times before, which is that when something didn't work, we don't necessarily have to do something drastically different. We just have to find the right way to fix it. What Hmac does is it takes as starting point the construction we saw that didn't work, and it then uses the same kind of idea as the encrypted CBC Mac, which also, if you remember, started from the basic CBC Mac, which didn't work. And that idea is that you kind of do it one more time. You take the output of the stage that didn't work and you repeat, you re-encrypt or something like that. So what Hmac does is it takes the first key, Ki, it will create from its key here two keys, Ki and Ko, the inner and outer keys. How does it do that? It takes this key here, and this key has length n. It concatenates 8b minus n bits of zeros to get a full block. And it then XORs in this constant. The other key, you take the same original key concatenated with zeros, and you XOR in a different constant. So you get two related keys, the inner and the outer. You concatenate the inner key to the message and run your hash function and get X. So that is doing a prior construct. That by itself would not give you a secure MAC. But now you concatenate, you prefix that with the outer key and rerun the hash function. And that's the Hmac result. So in code like this, you first compute this X and then Y like this. Okay, so it's an attractive design for a number of reasons. First, from the implementation perspective, it only makes black box use of the hash function, meaning if you have code already for the hash function, it's very easy to implement Hmac. And given the speed of hash functions, it was fast in software. And its security was also on a good foundation. It is, of course, subject to the same birthday forgery attacks we mentioned as existing for all iterated maths, but there is a security proof showing that there's no better attack than that. And a result of the security and implementation ease and speed led to quite widespread usage. The usage is both as a message authentication code and as a PRF. And in particular, it became one of the most widely standardized and used cryptographic constructs. It was and continues to be used in TLS, in many other protocols for secure channel establishment or connection across the internet. And there's a government standard. This is a wireless security standard, and so forth. And again, we can look at some of these standards. So for example, here's the government standard for Hmac, again, one of the FIPS, Federal Institute for Processing Standards documents, keyed hash function, keyed hash message authentication code. And it describes in full and detail how it operates. And it's kind of nice to see these things. If you look at the illustration here, it has some elements beyond what we said. For example, it allows variable key lengths and truncation of outputs and other things like that. This here is the RFC. This is the document that creates the internet standards put out by the IETF. And that's a very influential standard, and in particular influences many other ones. Okay, now the story of Hmac sort of evolved in an interesting way following this. So, and to discuss that, let's just look in slightly more detail at the security claims. So I mentioned that there is a proof of security. In more detail, what that says is that Hmac is a secure PRF. Of course, this requires some assumptions. So on the base primitive, so what are they? Well, one is that the hash function on which it's based is collision resistant. So that's kind of what people thought about hash functions at the time. But the other is an assumption is needed on the compression function underlying the hash function. So since the hash function is assumed to be in the MD style, there is a compression function. Now, think of that compression function as taking two inputs, the chaining variable and the message block. And think of the chaining variable as a key. When you do that, the compression function becomes a family of functions, and we can talk about its being a PRF. And the assumption is that it is a PRF. Okay? And with these two assumptions, Hmac was shown to be itself a secure PRF. Now again, at the time in the 90s, this assumption seemed natural and plausible, and this one was kind of novel. People hadn't thought about looking at compression functions as PRFs. And yet, in a few years, what happened is that these attacks we've discussed in our study of hash functions emerged, breaking MD5 and severely denting SHA-1 to the point where later it was also viewed as broken. And they show that the collision resistance property didn't hold after all. But at that point, Hmac MD5 and Hmac SHA-1 were out there in widespread use. And so people's first question was, once they saw these attacks, well, are the two Hmacs still secure? And that's not so easy to answer. The mere fact that you have attacks violating collision resistance of these does not immediately lead to attacks violating either UF-CMA or PRF security of Hmac using these hash functions. And people observed that. So that gave them some kind of confidence or strength that, okay, these are not yet broken, we can continue to use them. But the position was kind of precarious and not on good foundations, because the proof guarantee has now gone away. Not that the proof is wrong or non-existent, but if a proof makes an assumption that's false, it's just vacuous. It's not giving us any useful conclusion. So that state of affairs was resolved by a step on the theory side, a new proof was given. And what that said is the conclusion that Hmac is a secure PRF only needs this first assumption. The second one was never needed anyway, it was redundant. And this kind of helped things make more sense and also helped continue the adoption of these algorithms. Because the PRF assumption on the compression functions has not been violated. And current attacks do not contradict this assumption. And in some ways, it was an explanation of why the attacks violating collision resistance of the hash functions failed to damage the corresponding Hmacs. So, and Hmac thus continues to be in use, but nonetheless, caution says don't use Hmac with MD5. MD5 by now is so severely dented that it would be preferable, even if there's no convincing attack, to avoid this if you have a choice. Of course, if it's already embedded in some system, it's harder to do that. At the moment, it's not viewed as there being an immediate need to remove Hmac with SHA-1 from usage. But nonetheless, if you have a new application, it would be wise to use a strong hash function with Hmac, like SHA-256 or 512.